Good morning or evening. Our project is to use 1D Navier-Stokes shock tube simulation to benchmark quantum-assisted physically informed neural network. We are a team of 2. My name is Shan Zeng, and my team member is David Liu. This shock tube simulation including 3 Navier-Stokes equations, that is mass continuity, momentum balance, energy balance. The classic method uses an explicit Lax-Friedrichs stream to update the viscid flux, viscosity, and Fourier heat condition are handled implicitly using a backward Euler method. The time step is adjusted adaptively according to the CFL condition. And while the spatial domain is discretized using a uniform finite volume grid, finally mass conservation is checked for every generated scenario to ensure the quality and physical consistency of the simulation. The input are xt left-right pressure ratio, dynamic viscosity, initial left and right density, and initial right pressure. The output are the density, speed, and pressure. After shock tube simulation are completed, we use a full machine learning model to build surrogate model for the simulation. MLP, a classical PINN, a hybrid quantum classical PINN, and a fully quantum PINN. The main research question is, can quantum layer improve the accuracy and performance of PINN? The first 3 models use similar network structure with a 4 hidden layer and a hidden size of 128. In the hybrid model, select classical hidden layer are replaced by quantum layers, while the full quantum model does not use classical neural network layers in the machine learning model. We systematically vary several quantum design choices, including the data encoding method, training ansatz, qubit mapping strategy, number of quantum layer, and the position of quantum layer within the network. By comparing this configuration with the classical MLP and PINN baseline, we aim to determine whether quantum component can strengthen PINN performance and identify which quantum architecture provides the best accuracy. Here is the model structure we explained earlier. For the classical PINN, the input layer is followed by 4 classical hidden layers. The network predicts the physical variable, while the physical informed laws incorporate PDE residual together with the training data. For the hybrid quantum classical PINN, we maintain a similar overall architecture, but replace one or more of the classical hidden layer with trainable quantum layer. This allows us to investigate where the quantum layer should be inserted and whether it can strengthen the performance of the classical PINN. For the fully quantum PINN, both the input and target output are first mapped and encoded into quantum state. The encoded state then passes through a trainable ansatz, and that's for the input data, pass through the ansatz. After the quantum circuit, polymeasurements are performed to exact the required observations. We then calculate the quantum PDE residual and fidelity-based loss directly from the quantum representation. Finally, a classical readout and post-decoding step convert the measured quantum information back into the physical variable corresponding to the target state. A range of quantum data encoding strategies are tested to determine how the choice of encoding affects the accuracy of the performance of the quantum PINN. These include Unger encoding, 4-term Unger encoding, Z-term Unger encoding, dense encoding, octane encoding, IQP encoding, amplitude encoding, and FFT-based encoding method. Different variational quantum circuit ansatz are also tested to investigate how circuit architecture and qubit entanglement affect the performance of quantum PINN. These include U-ring, U4, U-alternate, efficient SU2, strongly entangling, NC-coupled, brick wall, and Hartwell efficiency ansatz. This ansatz provides different patterns of parameterization of single qubit rotation and entangling operation. The physics-informed loss is redesigned as a comprehensive physical constraint set rather than rely only on the local PDE residual. The loss incorporates global conservation, PDE conservation law, boundary condition consistency, initial condition consistency, and physical admissibility constraints. Together, these constraints encourage the circuit model to produce solutions that are not only close to the simulation data but also physical consistency with the shock tube problem. For the full quantum PINN, the physical loss is formulated differently. A linear combination of unitary is used to represent and combine different PDE residual components, and the linear combination of unitary constructor is implemented through a prepare, select, and prepare DAGA structure, where the prepare operation prepares the coefficient associated with different residual term, and select applies the corresponding unitary operator, and the pre-DAG complete the coherence combination. The fidelity loss is then incorporated to the measured and to measure the agreement between the predicted quantum state and target state. In this way, the quantum objective combines the physical PDE residual information with the state fidelity information, allowing the trainable quantum circuit to be optimized simultaneously towards physical consistency and prediction accuracy. Due to current computational resource and training time limitation, not all of the models have been fully trained, and therefore the result shown should be consistent. Here should be considered preliminary result. The figure here compare the predictions for 3 output parameters: the density, pressure, and the speed. The first row presents the ground truth shock tube solutions, and the second row shows the MLP prediction. The third row shows the classical PINN prediction, and fourth row shows the hybrid one, and the last row shows the full quantum prediction. From this preliminary result, the MLP, classical, PINN, and hybrid all capture the major feature of the ground truth solution, but the quantum does not. The fully quantum does not. From the figure, we see that the hybrid model slightly improved prediction accuracy compared to the classical model and fully quantum model. In particularly, placing the quantum layer near the first and last layer provide the greatest improvement. For both hybrid and the full quantum model, the choice of encoding and ansatz can significantly affect the prediction accuracy. For fully quantum model, the number of qubits used for feature mapping also has a strong impact. Therefore, careful selection and optimization of the model configuration are essential for achieving good performance. Again, we see that the hybrid PINN achieve better prediction accuracy than the classical model, while the fully quantum model perform worse. Conclusion and future work. We have found that the full quantum Q-PINN in the best sweat configuration reach only the correlation coefficient to approximately 0.78 on the test set, against the value approximate to the 0.9961 for the classical PINN and 0.999 for the hybrid QA PINN. And we also see that the choice of encoding onset, number of mapping qubit, and the quantum layer location can be also a significant impact factors for the precision accuracy of the PINN model. Because all the running tests has not been done, so future work we still needs to be studied for the fully quantum code. And mapping to larger qubit number seems to be the most important things to improve the accuracy. So we have not much data to check that. Thank you very much.